Hey everyone, Mr. Houck here. In today's video, we're going to be looking at some rules of exponents. So let's go ahead and get started. Alright, so we're going to start with the basic exponent rules. With the product rule starting off, if we are multiplying two of the same base, then we can go ahead and add up their exponents together and have only one base. Quotient rule, let's say we are dividing two things of the same base. So here A would be the base. Then we can subtract those exponents, always going top minus bottom. Okay. The power rule. If we have a base with an exponent being raised to an exponent, then we can just simply multiply the two powers, multiply the exponents. These two rules right here, the product rule and the power rule, they get confused with each other all the time. Notice here that we're multiplying two of the same bases together. Here it is a base with an exponent being raised to an exponent. So this is a power to a power. This is multiplying two of the same base together. Okay. Similarly, power of a product rule here. If we have a product of two bases on the inside of the parentheses and we're raising them to a single power, then we can go ahead and take this power and we can distribute it to each of those bases, A and B. All right, power of a quotient. If we are dividing two bases and we're raising them to a single power m, then we can go ahead and take this power and distribute it to both the a and the b, the numerator and the denominator. Now, an important note here that we need to be aware of with these two. Okay, so note. Notice that with each of these, when we're distributing this power that's on the outside into the inside, the only reason that we're allowed to do this is because this is either strictly multiplication or strictly division. This would not work in this scenario. Let's say we had something like this, a plus b to the m power. I cannot simply distribute the power of m to a and b because of this addition sign. This is not equal to a to the m plus b to the m. Very important to realize that we cannot distribute like this because of the addition sign. This is only going to work. We can only distribute these powers when it is multiplication or division strictly. Okay. Same deal if this was like a minus sign. I could not go in and distribute the powers and make it like this. Okay, not going to work. So don't do that. All right, zero exponent rule. Anything raised to the zero power is going to equal 1. Okay, negative exponent rule. Some base a to a negative power m is equal to 1 over, and then the positive version, a to the positive power m. Okay, and then we have our fraction exponent rule. If you have some base a being raised to a fraction exponent m over n, then what we can say is that the denominator represents the root that we're going to take, the nth root of a to the m power. Another way to write this, or a over, or a to the m over n power is equal to the nth root, write better root than that, nth root of a, all to the n power. So these two are equivalent to each other. We can either say the nth root of a to the m power, or we can say the nth root of a all raised to the m power. It kind of depends on what the problem is asking for. Sometimes, and you'll see it in some of the examples, sometimes this form is a little more advantageous to us. All right, so let's go through some examples. The first four examples here, examples 1a through d, are going to be examples that kind of hit at some common misconceptions and some common mistakes that students make. Okay, so we want to compare, in example 1a here, we want to compare 3x squared to parentheses 3x squared. So when we look at just simply 3x squared here, this is just 3 times x squared. Only the x is being squared, 3 times x squared. However, when we look at parentheses 3x squared, the 3 is being squared and the x is being squared. So parentheses 3x squared, this is 3 being squared and x being squared, which is 9x squared. Okay, so the difference the parentheses makes is very important. Example B, very similar. We're going to compare 4x to the 1/2 and parentheses 4x to the 1/2. So again, 4x to the 1/2 right here, this one is just 4 times x to the 1/2. And the 1/2 power is the square root. So this is just 4 square root of x. Okay. However, parentheses 4x to the 1/2 power, well, we can distribute this power, this 1/2 power, into the 4 and the x. This would be 4 to the 1/2 times x to the 1/2. Again, 1/2 power means square root, so this is square root of 4 times square root of x, which is 2 square root x. Okay. Next, we want to compare parentheses 2 plus 3 squared and 2 squared plus 3 squared. Now again, common mistake, and we kind of saw this up here. If we have two things being added, we cannot just simply distribute the power. You're going to see why with this example right here. So 2 plus 3 squared, well, parentheses first in order of operations, 2 plus 3 would give us 5, 5 squared would give us 25. Okay, versus 2 squared plus 3 squared. Well, 2 squared is going to give us 4, 3 squared is going to give us 9, 4 plus 9 gives us 13. So we can see that this does not work. 2 plus 3 squared, we can't just simply distribute the power 2 there to get this. These two are very different things, as we can see right here. First one was 25, second one was 13. All right, example D, another common misconception. One thing students love to do is they'll see a square root of two things being added together, and they'll just decide, let's split it into two separate square roots, square root of 36 plus square root of 64. Let's see if that actually works. All right, so square root 36 plus 64. Well, 36 plus 64 is 100. Square root of 100 is 10. Okay. Well, let's see what happens if we would have handled the square root separately, if we would have split it. Square root of 36 plus square root of 64. Well, square root of 36 is 6. Square root of 64 is 8. 6 plus 8 is 14. Very different things here. So we cannot just simply, take a sum underneath the square root. We cannot just simply break into two different square roots. It's not going to work that way. It's not going to work mathematically. These are two very different things. Okay, so that kind of covers some common misconceptions, some common things that students confuse. But now let's start doing some examples of our exponent rules. Okay, it's going to be a lot of examples, but they go pretty quickly. All right, example 2, we want to simplify each of the following. So here we go. -3 to the 4th power. All right, when you see a negative inside the parentheses, or honestly, if you see a negative something in general, we can look at it like this. This would be -1 times 3 to the 4th power. Because it's just strictly multiplication, we can distribute the power 4. This is now -1 to the 4th times 3 to the 4th. -1 raised to an even exponent is always going to be +1. 3 to the 4th is 81. 1 times 81 is 81. Okay, and let's compare that to -3 to the 4th without the parentheses around the -3. So again, we can look at this as -1 times 3 to the 4th. Well, notice that in this scenario, only the 3 is being squared, not the -1. So it's going to be -1 times 81, which is -81. So the presence of the parentheses around the -3 in example A made a pretty big difference. All right, part C. 2a squared b times 4ab squared. First thing I want to point out, when you have variables, when you have these bases, if you don't see an exponent, it's always a 1. So this is 2a squared b to the first times 4a to the first b squared. All right, when multiplying these, we can go ahead and multiply the coefficients. 2 times 4 is going to give us 8. But when we're doing a to the second times a to the first, that's going to be our product rule. So we're going to have a to the 2 plus first. We're going to keep the base the same, but we're going to add up the exponents. And then when we do b to the first times b to the second, same deal. It's going to be b to the 1 plus 2 power. Right? So this will be 8, a to the third, b to the third. All right, example D. Okay, first off, notice the 5 on the outside of the parentheses. One common mistake that students have made in the past is they'll go through and try to distribute the 5 to both these pieces. Let's say this 3 wasn't even here, okay? Let's say that exponent 3 wasn't there. You still don't distribute 5 to both the x squared and the y to the fourth. You would do that if there was a plus sign in the middle, then you could do that, but there's not. You can't do that. It's just 5 times this. It's literally, if the 3 wasn't here, it'd literally just be 5x squared y to the fourth. Okay, the 5 doesn't distribute that way. But let's handle the problem as it's written. So we have this power 3 right here. Power rule says that we're going to go ahead and take this 3 and we're going to distribute it to these two right here. So we're going to have 5 parentheses. With the power rule, if we have an exponent raised to an exponent, we multiply them. So 5 times x to the 6th, y to the 12th. And again, this 5 is not going to distribute. It's not going to distribute like that. It's just going to be 5x to the 6th, y to the 12th. All right, example E. All right, x plus y to the second power. Remember, with this addition sign in here, we cannot simply distribute the power 2 like that. It's not going to work. So this is literally x plus y times x plus y. Okay, x plus y times itself. We'd have to FOIL this out. Okay, so x times x squared, x times y, xy, y times x, it's going to be xy again, y times y, that's going to be y squared. Okay, so this will be x squared plus 2xy, there's 2 xy's, plus y squared. All right, part F. All right, so looking at this, common mistake that students will make. First off, they'll add the 2 and 7, which is fine. You should get 9. But it's x to the third and x to the third, but we're adding them together. If we were multiplying them, x to the third times x to the third, we would add up the exponents. But because we're just simply adding them together, they have this is a common term, x cubed plus x cubed. So this is just going to be 9x cubed. It's kind of like if I had said do 2x plus 7x, you would have just said 9x. So 2x cubed plus 7x cubed, that's just 9x cubed. Or alternatively, another way you could look at this is say, hey, there's an x cubed in common. I could factor out the x cubed, and that would give me 2 plus 7 left over, but 2 plus 7 is 9 x cubed. Okay, so you could look at it like that as well. All right. G, easiest problem on here, x squared y to the third over x to the 7th y, but the whole thing is being raised to the 0 power. If the whole thing is being raised to the 0 power, it's equal to 1. Nice and easy, we like that one. All right, H. We have some quotient rule going on here. We have a to the negative first, b squared c, divided by a to the 5th, b to the 6th, c to the negative 7th. Again, that c is c to the first. You don't have to write it there, but I'm going to write it there just for visual sake. So quotient rule saying, hey, if you have bases that are dividing, we go ahead and subtract the exponents, top minus bottom. So this is going to equal a to the negative 1 minus 5, b to the 2 minus 6, c to the 1 minus negative 7. Be on the lookout for these double negatives, right? It's subtraction, top minus bottom, and the bottom was already negative, so minus negative 7. Cleaning this up a little bit, a to the negative 6th, b to the negative 4th, c to the positive 8th. And typically, you don't want to leave your answers with negative exponents, usually. So we're going to take this a to the negative 6th and b to the negative 4th, the two terms that have negative exponents, and we're going to move them to the other side of the fraction, making this c to the 8th over a to the 6th, b to the 4th. All right, part I. Almost done with the front page. Okay, 2 times x to the negative 1st to the 5th power. Notice it is strictly multiplication on the inside, no addition or subtraction, so I can distribute this power 5 to the 2 and to the x to the negative 1st. This is going to give us 2 to the 5th times x to the negative 1st to the 5th. So this is going to be 2 to the 5th times x to the negative 5th. 2 to the 5th is 32 times x to the negative 5th. And this x to the negative 5th, because we were raising it to the negative power, is going to go down to the other side of the fraction, making it 32 over x to the 5th. All right, hopping over to the back. We want to take each one of these and write them in radical form. Okay, so n to the 4/5 power. If we have an exponent written as a fraction, remember the bottom part of the exponent is representing the root. The top part of the exponent is representing the power you're going to raise it to. So this could be equivalent to the 5th root of n to the 4th. Okay, or alternatively, we could have this as well. The 5th root of n, all raised to the 4th power. Either one of these are perfectly acceptable, so it doesn't matter which one you'd answer as. All right, part B. 10k in parentheses, all raised to the 4/3 power. So again, that 3 in the denominator, that's going to represent the root, the 3rd root. So I can write this as the 3rd root of 10k to the 4th power. Okay. And again, there's another acceptable version of writing this out as well. You could have the 3rd root of 10k and then that whole thing to the 4th power as well. All right, part C. 5x to the 1/2 power. Notice that 5x is not in parentheses, so the 1/2 power only applies to the x. And we know that 1/2 power means square root. So this is 5 times square root of x, or just 5 root x. All right, part D. We have parentheses 2p to the negative 7/5 power. I am going to take care of the negative part of the power first. So I'm going to make this 1 over parentheses 2p to the positive 7/5 power. So that's going to be the first thing that I do. And then now I'm looking in the denominator here, and I'm saying, okay, this is going to be the 5th root of 2p to the 7th. So now this is going to equal 1 over 5th root 2p to the 7th. Okay. All right, in example 4, A through D, now we're going to work in the opposite direction. We're going to take all these radical form answers and we're going to write them in exponential form. So all our answers are going to be have exponents that are fractions. Okay. So part A, the 4th root of k. Because the 4 is the root, we know that 4 is going to be in the denominator. And k is just to the 1st power. So this is k to the 1/4 power. Nice and simple. All right, example 4b. we have the third root of 5x, and the whole thing is being squared. So again, with this 3 being the root, I know this is going to be 5x to something over 3, and the whole thing is being squared, so 5x to the 2/3 power. All right, part C. 5x squared, we're taking the cubed root of that, so I know it's going to be 5x squared something over 3. Now, notice that this 2 is only applying to this x, so it wouldn't be like a 2/3 power here. If this whole thing was being squared, then it would be a 2/3 power, but this whole thing isn't being squared or cubed or anything. So this is just going to be a 1/3 power, so 5x squared to the 1/3 power. Alternatively, another way that you could write this answer is you could take this 1/3 and distribute it to the 5 and the x squared, because the operation here is multiplication. So you could say technically 5 to the 1/3 times x to the 2/3. This would also be an acceptable answer, but I'm perfectly fine with this answer right here. Okay, and then part D, 1 over the cubed root of 6x all to the 4th power. All right, so cubed root, so this is going to be 1 over 6x, something over 3, and this whole thing is being raised to the 4th power. So 1 over, parentheses, 6x to the 4/3 power. This is a perfectly fine answer. You could also say, because you have this 4/3 power in the denominator, this could also be 6x to the negative 4/3 power. That's a perfectly acceptable answer as well. So I'll box that one. All right, example 5, simplify completely. So these have some good examples, especially A through D here, 5A through D. Show the differences between, where the negative shows up and if there's parentheses or not. So 8 to the 2/3 power. Typically in the past you would have used a calculator probably to go ahead and calculate that, but this is a pretty easy one to calculate by hand. So we have this 3 in the denominator, so we have the cubed root of 8 squared. Okay, again, you could also have cubed root of 8 total squared. That'd be perfectly fine as well, it doesn't matter. Here, so 8 squared, that's going to be the cubed root of 64. And we're asking ourselves, it's a cubed root. So what number multiplied by itself 3 times would give you 64? Well, the answer there is 4. 4 times 4 times 4, that would give you 64. So there's our answer. All right. Now let's do negative 8 to the 2/3 power. So this is negative 1 times 8 to the 2/3. From the previous example, we already saw that 8 to the 2/3 power is equal to 4. So this is negative 1 times 4, which equals negative 4. Okay, now we're going to have the negative up in the exponent, 8 to the negative 2/3 power. Okay, well this is going to be 1 over 8 to the positive 2/3 power, so I'm taking care of the negative first by moving the 8 to the 2/3 in the denominator. But again, from example A, we already saw that 8 to the 2/3 power is equal to 4. So this is 1 over 4, and we're done with that one. Right, and then example D, negative 8 in parentheses to the 2/3 power. So a couple ways that we could look at this one. Here's how I'm going to look at it. I'm going to go ahead and say, okay, there's your 3 in the denominator, so we're looking at the cubed root of negative 8 squared. Okay, cubed root of negative 8 squared. Well, negative 8 squared is going to be positive 64, so cubed root 64, which is 4. Notice this still would have worked looking at it the other way. If I would have said cubed root of negative 8 quantity squared if I would have done it like this. Well, the cubed root of negative 8 is negative 2, but then negative 2 squared still would equal 4. So regardless of how you set it up into either of those two different forms, we still would have got the exact same answer. All right, part E, 405 x to the 7th to the 1/2 power. The whole thing is being raised to the 1/2 power, and 1/2 power means square root. So this is really just the square root of 405 x to the 7th. All right, doing square roots now. So 405, let's keep the square root for now. I'm just going to show you, as kind of a basic way to handle square roots like this. 405, we can see that it ends in a 5, so it must be divisible by 5. 405 turns out to be 5 times 81. And x to the 7th, well, if I want to think about, we're taking a square root, if I want to break up x to the 7th into a bunch of perfect squares. So x to the 7th could be x squared times x squared times x squared times x, right? And looking at this, let's look for our perfect squares, rather. 81's a perfect square, x squared is a perfect square, and we have 3 of them. So now, taking all these square roots, square root of 81 is 9, square root of x squared is x, but we have 3 of them. So x times x times x on the outside, that's x cubed. And then still remaining underneath is our 5 and our x. All right, so 9x cubed, square root 5x. All right, part F, a to the 5th, b to the 10th, c to the 6th, all to the 1/3 power. Okay, 1/3 power, that's going to be a cubed root of a to the 5th, b to the 10th, c to the 6th. All right, so I'm going to do something very similar to what I just did. I'm going to break this into cubes. Okay, so I'm going to say, all right, another way that I can write, it's a sloppy root, another way that I can write a to the 5th is a cubed times a squared. Another way that I can write b to the 10th is b cubed times b cubed times b cubed times b. And another way I can write c to the 6th is c cubed times c cubed. And again, the reason I'm doing this is I'm taking a cubed root. So I'm looking at this and saying, okay, well, the cubed root of a cubed is just a. So I have a perfect cube right here. A perfect cube, perfect cube, perfect cube, perfect cube, perfect cube. So cubed root of a cubed is just a. Cubed root of b cubed, and b cubed, so that'd be b, b, and b. That'd be 3 of them on the outside, so b cubed. And perfect cube of c cubed is c. We have 2 of them, c squared. Times the cubed root of anything that was still left underneath, a squared b. All right, so ab cubed c squared times cubed root a squared b. All right. Part G, x to the 4th, y to the 6th over y to the 8th, all to the negative 1/2 power. I'm going to take care of that negative part first. So this would be, I'll just flip this fraction upside down. So now I'm going to have y to the 8th over x to the 4th, y to the 6th, to the positive 1/2 power. So again, that's getting rid of this negative here. We can go ahead and I'm going to rewrite this a little bit here. This y to the 8th and y to the 6th, it's just going to be y squared. And I'm going to take this x to the 4th. I'm going to bring it up to the top as a negative x to the 4th. So I'm now going to have x to the negative 4th, y squared to the 1/2 power. And now I can take this 1/2 and distribute it here to the other powers, because again, the only operation here is multiplication. So that's going to give me power to a power, you multiply them, x to the -2nd, y to the 1st, and we can take that x to the -2nd, move it to the bottom because it's a negative exponent. So y over x squared. Okay, part H. 36 plus 64 to the 1/2 power. Parentheses first, so this is square root of the whole thing. Not 36, 64. Alright, so that's square root of 100 if you add those together, and square root of 100 is 10. Alright, one more type of problem that we want to talk about is actual solving equations involving exponents, okay? So when we are solving equations involving exponents, the goal is we want to try to get each side to have the same base. So right now, in example 6a, the base of the left side is a 2, but the base of the right side is a 32. It's 32 to the 1st power. So they have different bases. So I want to try to get them to have the same base. And what I'm thinking here is I'm going to rewrite this 32 as 2 to some power. Okay, so my left side will be 2 to the x minus 1st, and 32 is 2 to the 5th power. Now the bases are the same. If the base of each side of the equation is the same, then the exponents must equal each other. Alright, so now I know x minus 1 must equal 5. Add the 1 to the other side. X equals 6. Okay, and you can check it, of course. Plug in x equals 6 into the original problem. 2 to the 6 minus 1, well, that's 2 to the 5th. 2 to the 5th is 32. Check. Alright, so that's a pretty easy example. Now let's see an example that is not as straightforward as that one. So we have 27 x plus to the x plus 1st power equals 1 over 9. Okay, so again, we want to try to get each of these sides to have the same base. So here's what I can see. I can see that 9 is 3 squared. I can see that 27 is 3 cubed. So that's how I'm going to start. 3 cubed, rewriting 27 as 3 cubed to the x plus 1st power equals 1 over 3 squared. So now I'm saying I have this 3 as a base for both of them, but I still need to continue to rewrite this. So this is 3 again, 3 cubed, and let's go ahead and take this power 3 here, and this is a power to a power. This x plus 1 is the power we're raising this to, so we can multiply. So I'm going to distribute this 3. This is going to be 3 to the 3x plus 3 power equals, and this 1 over 3 squared, I'm going to rewrite it as a 3 to the -2nd. Okay? So now the bases are exactly the same. Base 3, base 3. I can take the exponents and I can set them equal to each other. So 3x plus 3 equals -2. Subtract the 3 over. 3x equals -5. Divide the 3. X equals -5 thirds. All right, last example. 5x to the 3/2 power minus 1 equals 14. So trying to solve here, we're going to do some of the usual equation stuff. Let's add the 1 over. So plus 1, 5x to the 3/2 equals 15. Okay, let's divide the 5 on both sides, that coefficient. Divide by 5. Now I have x to the 3/2 equals 3. Okay, so when we get to this point, how can we solve for x? Well, here's what I'm noticing. I'm trying to solve for x, which is x to the 1st. I have this 3/2 power. So what I'm going to do is I'm going to do a tricky little thing. I'm going to raise both sides to the 2/3 power. Because it's an equation, to maintain the balance of the equation, I have to raise both sides to this 2/3 power. Well, notice here, 3/2 times 2/3 is a power to a power. If I multiply these two together, I'm going to get 6/6, which is 1. So that leaves the left side is just an x, which is what I wanted. The right side, however, is just going to be 3 to the 2/3 power. Okay, and 3 to the 2/3 power, not really anything that we can do with that. You could rewrite it as the cubed root of 3 squared, which is the cubed root of 9 if you wanted to, but you can't really evaluate that it's going to be some kind of decimal. So this is perfectly fine to leave your answer like this. Also, one more thing before I cut the video short here. In the key to the notes, so if you go on eClass and you look at the notes, the key to these notes, I accidentally left this right here in this example, this example 5F. On the key to the notes, I forgot to put the cubed root there. This is what the answer looks like on the key to the notes. It needs to have this cubed root. It needs to be ab cubed c squared times cubed root a squared b. Okay, but that's been the notes for exponent rules. Go ahead and try the practice. The key to the practice should be up on eClass. Have a great day, y'all.